All right, I think the stream has started. Hello, everyone. Adam is somewhere in Europe this week. I'm not sure where. At some sort of cybersecurity conference. So I am filling in this week. We are going over memory corruption. As a reminder, we've got the last two modules, I believe, available until like the day before grades are due or something like that. I'm not committing to that. Whatever was previously said is what it is, but I'm pretty sure both these last two modules are due like right up till like through finals week or something like that. And so Adam covered a bunch of stuff related to web security. I am going to be covering stuff related to binary exploitation. He also talked about some of this stuff last Wednesday, talking especially about shell coding and this idea of spawning a shell. I am going to get more into this memory errors world of things so that all makes sense. Before we continue, is there any questions that anyone has about anything? Yes. Sure. December 10th. All right. Sounds like Adam has previously said December 10th. I assume he has a Discord announcement. If it's at all unclear when things are due, message in the 365 Discord channel. We'll make sure it's super clear to make sure there's no confusion on that. Okay. Any other like course logistical questions? I think this is the last week, right? This is, and then it's finals week, but we can't teach during finals week because there's finals that happen at random times. Unfortunately for you, there's no final in this class. You'll have to just suffer through your other finals. Okay, let's go ahead and talk about memory corruption. Let's make sure we got the Twitch chat open in case we get a message there. Okay. I guess, does the Twitch stream working? Does anyone know? Maybe someone's open. Oh, let's check real quick. We will just make sure, since I haven't done this in forever. College, looks like it's going. Is there audio? Yep, cool. All right, let's continue on then, and let's talk about memory corruption. So I am going to start up memory errors level 1.0 in practice mode, just as a way of getting an environment, and we are going to generate a program and talk about memory layout. If you want to understand memory errors, you need to understand what's going on in memory for a program. Okay, so we're going to SSH in. Cool. Let's launch this. 1, 2, 3, 4, 5. We'll do that. We will start up a random directory. And we will start writing a random program, hello.c. And then cd hello 1, 2, 3. Okay, so let's write a program in C so that we are all on the same page. Hopefully everyone is familiar with C enough to understand what's going on here. Okay, so let's create a buffer of size 8. So this thing can hold up to 8 bytes, as we're all familiar with. And then let's go ahead and do something insane, which is to read well past 8 bytes into this buffer. So this is a classic demonstration of a buffer overflow, and we're going to use this at first to understand what's going on in memory. Okay, so we're just going to arbitrarily decide to read 256 bytes. Hopefully it's clear to everyone, right? This is not a good idea. This is a buffer overflow, and you might be thinking to yourself, how would I ever write a program that looks like this? This is super dumb. Turns out in very popular software, browsers, the kernel, all sorts of things, this sort of error still does occur. It looks dumb right here because this program is 2 lines of code. But if you have a program that's 10 million lines of code and you're passing around pointers and you're not passing around a size and things get mixed up, once you add a lot of complexity to a program, it is very possible to make a mistake that looks like this. But for now, we're going to keep it simple, 2 lines of code. It looks dumb, but it happens. Okay, we are going to compile this program, and we're going to compile it. We're going to name it hello, and we're going to add 2 extra flags to GCC. So if I didn't add these flags, right? This is going to compile. It's going to complain about read. But it will compile. We're not going to use the default compilation options right now. We will get to default compilation options right now, but what we're going to do first in order to understand what's going on is we're going to disable two prevalent memory corruption preventing things. The first thing we're going to do is we're going to write -no-pi. So we'll talk about this in a second. And then we're also going to do fno stack protector. Let's see if I typed that correctly. Looks like I did not type that correctly. Fortunately, oh, it's just that. Okay, so 2 extra flags to GCC. We've got a program. We can run this program. Actually, to make it clear the program runs, we'll also add some sort of like puts hello world, right? Nice and fun. And maybe then we'll also do puts buffer. Okay, so let's compile this. Let's ignore our warnings. Well, you know what? Let's be good. We'll include, hopefully this is just standard IO. Let's see if that is just in fact standard IO. Read is, does anyone know what read is? Is it standard lib? Let's see. But it's the Unix one. What is the Unix one called? Let's see here. Does anyone? Nope. Oh, did I typo? No, I did not typo. Does anyone know what the include is for read? Any people that like C? No, we don't have any people that like C here. Include GCC for read call. Let's see. I don't know. Bunch of words. That is definitely what it is. I knew it was Unix something. unistd.h. Cool. Okay, now we don't have warnings. Didn't really matter, but we're going to be proper here and we're going to compile without warnings. Okay, now if we run this program, so it's called hello. As we expect, it says hello world. It is currently hanging, waiting for input. It's stuck on that read system call. If we say hello to it, it now echoes back to us what we said, and it will say hello as well. So very straightforward program. Hopefully we all know the meaning of this program. Let's go ahead, though, and let's launch up GDB to further investigate this program to understand what's going on. Okay, so we are going to start the program. So we just type start. The program has started. We have a whole bunch of instructions that are about to run. So we see this NBR64. Hopefully you've maybe seen this in the reverse engineering module. You've seen this NBR64 all over the place. For now, just think of it as like, hey, this is the beginning of a function. And then we set up our stack. Eventually, we call puts. And in fact, if we want to see maybe all of this function, it's really not that complicated. I know assembly is probably still scary to many people. You know, it's like, way worse to look at this than to look at C. There's really not that many instructions here. It's kind of straightforward. I believe that you all could write this in assembly if you had to. So what we have here is the function starts up. So these 4 lines that I've highlighted here, this is the prologue. So the program starts up. We save the base pointer. We move the stack pointer into the base pointer, and then we sub hex 10 from RSP. So what all of this just did is we created a stack frame for ourselves. We've got 16 bytes to work with now as our little stack frame thing. Then we load into RDI. So the very first argument to any function call is RDI. What we load is this address right here. If we're curious about that address right here, if we do x/s, we see that is at that location in memory. We could print it as not a string. We could print it as 20 bytes or something like that. 20 bytes. We've got the content hello world ending with a null byte. Okay, and then continuing on with this program, we take from RBP minus hex 8. So we do this LEA instruction. I don't think we've talked about the LEA instruction a whole lot in this class. Maybe you recognize it, maybe you don't. What we're doing here when we do this LEA instruction is we're just taking this address. So normally you see these square brackets and you're pulling out of memory. When you see these LEA, it kind of like cancels out the square brackets in a sense, and we're just taking this location. So we're going to take this location in memory. So this is on the stack, RBP minus hex 8. This is a local variable, and we're storing that into RAX. Then we're going to put hex 100 into EDX. What is hex 100 as decimal? Right, that's our 256. If we think back to our program, 256. That is ending up into RDX or slash EDX, same thing in this case. We're taking that location in memory. We're putting that in RSI. So that location in memory, this RBP minus hex 8, guess what? That's our buffer. It's located somewhere on the stack. And then we take 0 and we put that in RDI. Why do we put 0 there? Because we're reading from standard input and we specified 0. And then we call read. Then what happens? We take that location in memory once again. It's kind of like a little bit dumb, right? It's kind of already sitting in our SI, so we could have done this a little bit differently, but it's uncompiled or unoptimized code. We take this location on the stack one more time, put it in RAX, and then move it from RAX into RDI, and we put stat. Finally, we put 0 into RAX, we leave ret, and this is the idea being in C, if you're unfamiliar, there is an implicit return 0 at the end of a function. If you say that it is an int and you don't put a return statement, there's an implicit return 0, so that's what this is. So really not too complicated of a program. This is the assembly, this is the C, this is kind of the back and forthness of it. Okay, let's watch now though. This location in memory. So I've got it set up. I did display 8i RIP. This means is every time I step an instruction, we're going to see 8 instructions, the next 8 instructions in code. I'm also going to do display slash, let's see here. Let's say 32x at RBP minus hex 8. Let's see here. I think, is this going to do what I want? No, it is not going to do what I want. I think I need a, can I unset to? Nope, we're going to start it again because I don't know how to unset that. Start, display 8i RIP, and then I think it's going to be display like 32 bytes at RBP minus hex 8, but we're going to put a star there. I think this is the right syntax. GDB is like a language in and of itself. Oh, we need $sign. Cool. It's not happy with it right now, but I think it will be very soon. So let's step in instructions. So we just executed that NBR64. I think the reason it's complaining is RBP is currently 0. So we're basically doing a null pointer dereference-ish. And once we get RBP, it'll be happy, hopefully. Or is it? X32 dx RBP minus hex 8. Maybe we're going to have to manually type it. Yeah. Oh, it says a generic pointer. Can we say this is a character pointer? We're going to manually type it instead. All right. We're going to ignore that display command. Start display 8i RIP, and we're going to start stepping. So where are we going to step in order to understand memory? We're going to step all the way up to our read instruction, or our read system call. So if we look at this, we can see this is where read happens at main plus 41. Let's break at main plus 41, and we will continue to that. So now we're about to call read. The thing that we're super interested in is this RBP minus hex 8. This is a location in memory. This location in memory is on the stack. We look at the value of RBP minus hex 8. It is this value. If we look at 32 bytes there, right, it is currently this. So this is 32 bytes of memory right at this location. And as soon as we step, well, actually, we didn't want to step. We wanted to, instead of SI, we wanted to do NI to go over that call. So we're going to finish this call. As soon as we go past this read call and we type something to it, so let's say hello, we're now at the instruction just past that call to read. We're now at this load effective address. Let's look at memory one more time. So it now contains this right here. Maybe you're familiar with ASCII at this point to some extent to know that, hey, this looks very ASCII-like. And if we x/s that RBP minus hex 8, so instead of viewing that as a bunch of bytes, let's view this as a string, right? It is hello new line character. Okay, let's keep going. We are going to step instruction one more time. Step instruction one more time. We're not going to pay attention to this puts. We're just going to go next instruction to not jump into that call. And then we see 0 goes into EAX. And then we're typing or we're running leave. So what this is about to do is this is about to change our stack frame back to how it was before we started. So if we look at RSP, RBP, and we step, that is going to have changed our values, right? So RBP is now back to what it was at the beginning of this function. It was 0 initially, and RSP is back to what it was at the beginning of this function. And now we're going to do ret. And ret is kind of the super magic instruction when it comes to memory corruption, at least for what we're going to be talking about today. Ret is like everything. When you see ret, this is the instruction that is going to change our instruction pointer. How is it going to change our instruction pointer? The way that it's going to change our instruction pointer is it's going to look at the stack, and it's going to basically just do pop RIP. So if we look at the stack, the very top of the stack, so XGX RSP, this is going to print as a 64-bit value at the top of the stack. We have this value right here. Code is about to continue executing right here once we do this. And one thing to notice is that this location on the stack, so this thing that's on the stack, right, 7FFFFFF, E548, this thing is close to, did I get a print of that? So this value right here, right, RBP minus hex 8 from the beginning. If we take this and we subtract this, probably go the other way. Hopefully, maybe you know 2's complement, right? That's looking like a negative value. These are 10 bytes apart. These are just hex 10 bytes apart. So this thing right here that's sitting on the stack, and we're going to see in one moment when I do a step instruction, this determines where code the next instruction will be executing once we execute this ret instruction. And this thing is stored right next to our buffer. These are like super close on the stack. In fact, let me, maybe we'll do something like this. We have this thing right here. So this value right here is on the stack. And then we'll say something else is on the stack. Actually, instead of doing it this way, let's actually just look at the whole stack. Let's look at X20BX or 32BX of this thing right here. So this thing right here, which was our hello, remember, we do X/S, this is our hello. This continues on all the way up to 548, right? And this is right here. So if we think little endian integer, these bytes are stored backwards. This value right here is an 8.3. This value right here is an 8.3. This is a 2.0, 2.0, DF, right? It's stored backwards. Alternatively, instead of printing it as 32 bytes, we could print it as 4 giants. Weird terminology. I'm not sure why it likes that terminology, but that's what it is. We can see that our hello is kind of embedded in this first 8-byte value, and our thing that we're about to continue executing is right here. So let's go ahead and just prove to you all that if we do a step instruction, this is where we're executing next. We do SI. Look at this. So maybe you've never stepped past the end of main before when you're writing C. It turns out main is not actually the first thing called. It's not the beginning of the program. libc start main, well, that's not the beginning either, but libc start main calls main. And so when we return from main, we're back into libc start main. The specifics of libc start main, it doesn't really matter. It's a function in libc that calls main. it doesn't really matter for us, but this is where we're returning control flow to. And the reason for that is because this was the value on the stack, the very top of the stack, when we were doing that ret instruction right here. This is it. So this is like the most important information to know about control flow hijacking, as we're about to see here in a second, that if we want to modify where the program is going, the thing that we're attacking is this value right here on the stack. This is everything right here. So let's do that. Let's start the program again. And we have a breakpoint set right at main plus 41. That's where we call read. This time we are going to continue. And what we're going to do is we're going to go over this call. So next instruction, it's looking for our data. We did hello before. So hello definitely fits within our 8 bytes that we're asking for. But we're willing to read up to 256. And as we said, right, we had those 8 bytes that is this buffer. Kind of semantically, that is the buffer. Then we had another 8 bytes, and then the next 8 bytes was where our control flow is going to. So let's just send a whole bunch of A's to kind of demonstrate this. Or maybe more specifically, I'll do 8 A's, then 8 B's, then 8 C's, and so on. And my goal here is going to be to put 8 A's right here, 8 B's right here, and then 8 C's right here. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And now if we look at the stack, so 32 bytes, well, let's do 4 giants again, at RBP minus hex 8, right? We have a bunch of A's here, a bunch of B's here, and then a bunch of C's right here. And then one other thing doesn't really matter here, but we had a new line character. That new line character did end up right here as well. Okay, so now let's keep stepping through this program. Back to that leave ret again. We'll go over this puts. We can see something interesting happen. When we did puts, it printed out a bunch of A's, a bunch of B's, a bunch of C's, and then a new line character. And then it also printed like this. So as soon as you're seeing this, I didn't type this, but it's printing this out to me. We'll see why in a second. Actually, we don't even, let's see why right now. Let's look at, so we were looking at these values. How does puts know when to stop printing? Does anyone here know how puts stops printing? What is it looking for? Yeah, a null byte, exactly. So what it did is it printed 8 A's, then 8 B's, then 8 C's, then it printed a new line character. You can see that we start a new line. And then what it did is it printed C6, FF, F7, FF, 7F, and then there's a null byte right here. So that's what these characters are here. I don't know if that exactly is, I'm seeing like 4 things here. I don't know if that corresponds exactly. Things might like coalesce into one weird question mark thing. But if similarly, if we do x/s right here, which also just goes off that till a new byte semantic, right? We can see here, in this case, GDB likes to print this as octal. For some reason, it decided octal is the cool backslashing format for this. And it just goes all the way until we have a 0, 0. Right? That's kind of how that works. So we are now going to step, and we're going to step. And now, as I said before, the location that we are going to execute next after we go through this ret instruction is whatever the value is at RSP. So the value at RSP right now, the value on the top of the stack, ret is just pop RIP. It's popping into the instruction pointer. This right here is 43434343. So if what I'm saying is true, which unless something dramatically changed in the last week, what's going to be executing next is 434343. We're not going to see when I do SI that we're executing back in libc start main. So let's do SI, and, well, it didn't get to SI. We got program received sig_seg_v segmentation fault. It is crashed. The program is crashed. CCCC is not mapped. If we do info proc mapping, we can see all of the memory mappings. If we wanted any chance at continuing execution, we needed something to be in one of these memory mappings. So before we had something in this libc, somewhere in libc, specifically in an executable page of memory. Alternatively, if we had something that was in an executable page for our hello program, or even LD would be fine, we needed an executable address in memory in order for us to continue executing, and we did not. So we got segmentation fault. That means a bad page was just accessed and we are crashing the program. Okay, so here is an interesting effect of that. We just showed that we can make it so that the program crashes. But what if we don't want the program to crash? I said already that this is like the crucial detail and information to control flow hijacking. Let's do control flow hijacking. Instead of setting it to a bunch of C's, so we just previously set it to a whole bunch of C's and then we crashed, let's set it to somewhere where we're not going to crash. That code exists and that code can start running. And a very simple thing that we can point at right now is main. So if we print main, right, it's at this address right here, right? We already saw the instructions of main. Let's go to here instead. Let's go right back to the beginning of main and see that, hey, can we actually do control flow hijacking? Before we do that though, there's one tiny little annoying like tooling issue here, which is the way that I've been interacting with this program. I've just been sending A's and B's and C's. If we're lucky, this would be ASCII, but I don't think we're gonna be lucky. I guess we can check. If we wanted to send this, so the first one is looking like ASCII. So this 56, 0x56, that is a character. So if we sent a capital V, we would be doing this 56. But then the next thing we need to send is this 11. Yeah, see, this is not an ASCII printable character, so we're already screwed. But let's just see the last one, which is a 40, an @ sign. So if we didn't get so unfortunate with this hex 11, maybe we could have manually typed it out. We could have printed like @V or something and overwritten that address and code would start executing there. Unfortunately, I don't have the ability on my keyboard to type \x11, which is, it's just one character. I know it's printing it to you as 4 things. This is just a backspace or / encoding mechanism here in Python for displaying that. We need some other way to do this. So let's, instead of running this in GDB real quick, or let's see here. What we'll do is we'll still use GDB. We'll write this out to a file though. So I am going to cd into hello123. I am going to open a file called payload. I'm going to write binary to it. And what I'm going to write is, let's start with what we had before, make sure we're not messing anything up here. Let's do 8 A's again, 8 B's, and 8 C's. And this is, we'll make sure these are byte strings just because we said we're opening up for writing bytes. If we want to write bytes, we need byte strings in Python. For literals, you put a B in front of it. Let's do that. Okay, so now if we cat payload, right, we have 8 A's, 8 B's, 8 C's. Let's go ahead now and continue using GDB. But what we're going to do is we're going to redirect standard input. Instead of standard input coming from, my terminal here, right, if I do cat or ls, al, proc self, fd, whatever, right, currently standard input is pointing at my terminal. Let's make standard input for this program when it starts up the program. Instead of pointing at the terminal, let's point at that payload file. And the way that we can do that in GDB is the same way you do it on the shell. It looks slightly different because we're typing run, but it's still just this less than character. If we do run less than payload, well, it ran through the whole program. We didn't have any breakpoints and the program crashed. So we know that we did something right here. Let's look at the top of the stack, right, 4343. So we just ran through without breakpoints, crashed again. So this is a good sign. Let's now write something else, though. Instead of these 8 C's, let's write the address of main. So X8I RIP, or main. This address right here, this 401156 thing. So you want to write this thing. Remember, even though it's showing this to you as like 3 bytes, this is an 8-byte value. An address is 8 bytes, so we need to write out all 8 bytes. So we'll kind of do this like manually for a second here. I'll show you a better way, or a less error-prone way to do this here in a second. This is how we would type that out, right? Remember, it's a little endian integer. It's backwards, basically. 5, 6, then 11, then 40, and then 1 null byte, and then 4 more null bytes. 2, 3, 4, 5. Wait, did I just miscount? See, this is why I never do it this way. 4, 5, 4, 5, 6, 7, 8. Okay. And if I, oops. This should say 24. Okay, we wrote 24 bytes. We did it right. It's a nightmare to write this out by hand, but we're struggling through it. It's really not that bad. Let's start the program again. And what we're going to do is, instead of run / payload, let's do start less than payload. So this is just going to start up the program, start at main. Okay, so we've started the program. We have a breakpoint set. Well, maybe we don't. Break main. Info B. Okay, so we have a breakpoint set at main. Let's look at all of these instructions. Let's break right here at this ret. Let's continue to that ret. So we can see it says hello world A B B B B B V at the way that it's displaying it. We lost that \x11. It just didn't show it to us. It didn't do a question mark either. Sometimes how it prints these non-printable characters is kind of random-ish, or at least I don't know the pattern in my head. And if we look at the top of the stack, right, we're about to execute this ret instruction. We're about to execute ret, and if we look at the top of the stack, let's see here, we can do x, gx, rsp. This is now pointing here. It's not 8 C's. It's not somewhere in libc start main. It's this thing right here. And if we do step instruction, we're back at the start of main. Look at this. I didn't even rerun the program or something in GDB. No, we are actually back at the start of main. And we are, if we continue, we are printing hello world again. And then, I don't know, I think it probably went and read the file again, and there weren't more characters in there. And I'm not sure exactly why we ended up with a bunch of B's here and then this. We could step through it if we wanted to see what happened there. But this just worked. And if we want to look at this outside of GDB, we can run hello payload. And look at this. It prints hello world. It prints stuff. Prints hello world. It prints stuff. And then it seg faults. So we just hijacked control flow of this program. If you read this C source code, I mean, probably you would notice there's an issue here. Like, why are you doing this? But maybe you wouldn't realize how bad this is. This is how bad it is. Like, this program should never print hello world twice, but it just did. And we segmentation faulted as a result because, I don't know if it read up to the end of payload again. I guess we could try doing cat payload into payload. So now we have, wait, what? Okay, well, we'll use Python and write it again. I don't know. If we do this again, let's see if it runs through again. I actually have no idea what's about to happen here. We'd have to step through the logic, but let's write our payload out twice. Oh, you know, the issue is that won't work, and the reason that won't work is because we're willing to read up to 256 bytes in one read, so it'll read all 48 of those bytes in one go. So if we run this, right, it just does that again. If we want it to work for real, though, what we can do is we'll say payload equals oops. All right, apparently I cannot copy on my keyboard. Okay. And then say write payload, that writes 24 bytes. What we can do is we can say payload equals payload.ljust. We're going to like left justify this thing. And what we're going to do is we're going to say that this thing should be 256 bytes long. And we're going to pad with null bytes. So if I print this now, just because I don't know how many of you are super familiar with Python, but what this just did is, right, it put our thing and then a bunch of null bytes at the very end. That should be fine. And then let's go ahead and just write the payload twice. So the reason I'm doing this just to demonstrate, I think we can get a third hello world if we want. It's doing 256 byte reads. So it's going to read 256 bytes the first time and then 256 bytes the second time. So we need to pad that out to fill out the whole 256 so that the next 256 bytes start with this AAA pattern. Let's see if we get a third hello world. Yes, see, right, we got hello world this, hello world this, hello world this, and we're just like keep looping the program. If we wanted to, right, we could, do this 20 times or something. I don't know if we're going to run into issues at some point, but no, it looks like we're good to go. We got 21 hello worlds. So this is control flow hijacking. All we're doing is there is a saved instruction pointer somewhere on the stack. Our buffer is somewhere near that saved instruction pointer because our buffer is also on the stack. It's a local variable on the stack. And by reading past the end of this buffer, we're reading all the way up into the saved instruction pointer and overwriting that. And this is what this enables. So does anyone have any questions about this? Why this works? Is there anything that doesn't make sense about this? This is like the basis of common memory corruption vulnerabilities. And then it just gets way more complicated than this because you don't always see patterns like this and you don't always see GCC compiled like this. So we'll deal with that in a second. Any questions? No. Okay. One other thing I'm going to show, we use GDB to print out the address of win to get that, or to get the address of main. Let's switch it to win. Well, first, let's obj dump dmintel grep main. Hello. Right, so this was this address. So a few things I want to show you. Instead of typing this out manually, what we can do is we can do pwn.tools so you'll probably be using pwn.tools in this module, and we can talk about pwn.tools as we go. One of the very useful things within pwn.tools is the ability to have this p64 function. So this p64 function, it'll just take, oops, I guess we need to make it 0x, whatever. This will just do what we did by hand. It manually, does the reverse. We don't have to do it by hand. It's the length of this thing. It's 8 bytes. P64 just means packet 64-bit. It's a little endian integer, P64. Super useful thing. And then what we can do instead up here is say P64, this value, right? It's a little bit nicer. Same idea though. I mean, you could do it by hand if you really want to, but this is often very convenient. P64 packet as a little endian 64-bit integer. The next thing I'll show you though with pwn.tools is let's communicate with the process. So we can use pwn.tools to communicate with the process. I'm going to do from pwn import star. And then we've got this payload thing. And we're going to do, we're going to start up the process. So we're going to do challenge, or we're not going to do challenge. We're not working on a challenge right now. We're going to do hello. And we'll say that this is some variable p. Let's run that so you can see what just happened. There we go. So this tells us there's debugging output, nice useful information. It says, hey, I just started up a local process called hello. You'll notice that it didn't say hello world to us like it would on the shell. If we wanted to see that message, what we could do is we could do p.readLine. This prints to us one line worth of output. Then we could do p.write our payload. And then we could do p.readLine again. And we would see this. And then we read again, and we get our other hello world, right? Because we went back to the beginning, and now there's nothing left. And well, we could do, if you think about it, it just loops back to the beginning. We sent it our payload once. If we sent it like a single A or something, and then we read, we get this, and then it crashes. So this is kind of like interactive-ish. If we wanted to like script this out though, what we would do is we could say like p.readLine. So that'll read one line, and then p.write payload, and then p.readLine, p.readLine, p writes single A, p readLine. And I'm just thinking through like how this would all be coming to me. And then I could do like p.poll, and this will just wait for the process to exit, or let's do p.wait. Yeah. So that waits for the process to exit. We can see seg fault. If we wanted to, we could print all of these things. I don't know. We could do whatever we want. This is how we can programmatically interact with the process. So realistically, all we really care about is p.write payload. In this particular case, we don't really care about reading. Sometimes it is useful to think about reading, but there we go, right? Same idea. We just never read anything. Okay. So that is a basic gist of pwn tools. The next thing I want to show you is, you can imagine, let's start by saying, hey, there could be some win function. In these challenges, there will be a win function, or at least I think in almost all of them, there'll be a win function. For the memory corruption ones, let's just write some sort of random function that says, hello, you won. Oops. Here is your flag. This is a fake flag. Oops. Of course, the challenge, the way it's designed, you'll see it has like, here's a real flag. And let's do that. So let's recompile this program. Oops, we messed something up. Cool. So let's rerun it. Hello, test. Of course, we think to ourselves, this win function should never be called. Main never calls this function. If you compile this program with optimizations, the win function won't even appear in the binary because the compiler will be smart enough to say, hey, win is never called, so let's just delete it. But we're not running optimized code, so the win function is in there. And if we look at our program, let's see here. We'll just go back to that. We saw that main has now moved. That's kind of maybe one important detail. Before it was at 5.6. Now it is at 7.9. Main has moved around. And we also have this win thing that is located here. So let's just take our previous exploit and see what happens. We'll do p.readAll s. I don't think we want to write again. And let's switch out this address. So we're kind of assuming here that our stack hasn't like shifted around or something, that for some reason the compiler decided that local variables needed to be moved, that this buffer still is at RBP minus hex 8. Obviously, we know how to reverse engineer if we're unsure of that. We could confirm that it's still at RBP minus hex 8, and it is in fact at RBP minus hex 8. A useful tidbit here. So I said that when we're going through this ret instruction, that the saved instruction pointer is at the top of the stack. Well, relative to like the inside of a function, that top of the stack is always at RBP plus hex 8. So RBP plus hex 8, when you're like thinking about offsets, when you're in here and you're like, what's the difference between this local variable and my saved instruction pointer? The saved instruction pointer always RBP plus hex 8. So you can think the difference between RBP minus hex 8 and RBP plus hex 8, that's 16 bytes. That's why we sent 16 bytes of nonsense. And then the next bytes were the thing we're overwriting, which is the saved instruction pointer. So this should still be just 16 bytes of nonsense. And then we're overwriting the saved instruction pointer. Let's do that again. And we don't actually care about this ljust thing, so we'll just get rid of that. And we'll do that. So we can see it says hello world. It prints to us what we said. Then it says, hello, you have won. Here is your flag. This is a fake flag. Well, it's kind of like clear to see. It's not too difficult. Once you have a memory corruption issue and you're able to overwrite saved instruction pointer, it's like relatively straightforward to do this, right? We just had to compute that this is 16 bytes that we need to send of nonsense. You could do that statically. You could do it dynamically. There's a whole bunch of ways you could do it. I'll show you another way you could do it that's kind of interesting. If you do, pwn.tools has this other capability, which is called cyclic. So if I do cyclic of, let's say, 64, this is this weird cyclic pattern. So you'll see it's like 4 A's, then a B, then 4 A's, then a C, or 3 A's, B, 3 A's, C, etc. It's this like cyclic pattern. What I can actually do, let's see here. Yeah, you'll see I have all these core dumps, and that's what I was curious about. I'm going to delete those real quick. If I send as my payload equals P60, or not P64, cyclic of 64 bytes, or maybe we'll do 256 because we know it's reading up to 256 bytes. If I send this payload, the program is going to ultimately crash. We can see it like says hello world and then part of this cyclic pattern. If we look, we now have a core dump. So this program just crashed. We sent it 256 bytes. We overwrote the saved instruction pointer. We overrode it with effectively 8 Cs. It's not actually 8 Cs. It's somewhere in this cyclic pattern. And we got a crash. When we crashed our program, we got this core dump. And if we look at this core dump, we have a number of ways we can look at this core dump. We can do GDB hello and then core blah, blah, blah. And this just pulls up the program at the state of the crash. So we can once again look at where we are. We're at this ret instruction. This is where we just crashed. And if we look at xgx RSP, we've got this value right here. And if we take this and we go back to pwn.tools, or Python in this case, we can do cyclic underscore find, and we can just pass it this value, and it says, hey, this was 16 bytes away. So there's like all sorts of ways to figure out what your offset is. You can do it statically, you can do it dynamically, you can do it like through core dump introspection using the cyclic pattern thing. Either way, we just need to know the offset from our buffer. How many bytes do we need to write until we're overwriting the saved instruction pointer? This is another way we can do that. Okay, the next thing I want to show, so we've seen now that we can call into win. Let's start dropping away some of these mitigations. Or let's start adding back some of these mitigations. So there's 2 mitigations that I disabled that are normally on by default. There's this thing called PIE, which is a position independent executable, and there's this thing called stack protector. Both of these prevent this from happening in very different ways. So let's look first. Does anyone have a preference? Does anyone want to look at the PI or the stack protector first? No one's got preferences. Let's look at stack protector first. All right. So stack protector, what this is going to do, let's go ahead and not challenge. You keep thinking challenge, not win. Hello. What this is going to do is it's going to modify and add instructions into our code. It's going to add instructions up into this prologue, and then it's also going to add instructions into this epilogue. And what it's going to do is it's going to try to protect this saved instruction pointer. Let's see how it does that. So first I'm going to copy this just in case we want to reference it later. Yeah, let's go to Scratch. Let's get rid of that. We'll keep this in case we want to refer back to it. Okay, and then let's compile without that -f no stack protector. Let's give ourselves the stack protector back. And if we obj dump this, this is how it has changed. This instruction, these 3 instructions just got inserted. We'll explain those in a second. And then these 4 instructions at the bottom also got added. So we just gained like 7 instructions. So this right here at the beginning, right after we set up our stack frame, so we set up our stack frame whenever we subtract RSP at the beginning, we're basically allocating 16 bytes for ourselves on the stack. What this has done right here is it's pulled this value out of memory. And it's a weird memory access. You probably haven't seen this before. Or maybe you quasi did while you're doing the reverse engineering. It just didn't make any sense. We pull out of fs colon hex 28. So what this is there's like this, I guess we can start up gdb, hello, start, print. That doesn't actually let me see it. Wait, I didn't. Print. Is it going to let me do this? No, it's not going to show me this fs value. It's another register, basically. It's a segment register. So it's the F segment register. It doesn't really matter. It's just, think of it as another register. And let's look back at the obj dump. It's just somewhere in memory. And it happens that an important property of this somewhere in memory is it's a somewhere in memory that rarely gets accessed. There's reasons for that. It's a kind of special region of memory that gets set up for the program. And what's getting pulled out of there is a Q word. So 8 bytes of memory just got pulled out of this like magic space in memory. We'll just say it's the magic space in memory. If you're curious about the details, maybe we can talk about it on the Discord or something. It's kind of a little in-depth, but this other region of memory, we just pulled out hex 28 bytes and we threw that into RAX. And then because this is unoptimized assembly, we take that. Well, actually, I guess you couldn't do memory into memory, whatever. We put that into RAX, and then we put that into RBP minus hex 8. So if you ever see RBP minus something, this is a local variable on the stack. And we did not create a local variable for this thing in our C program. The compiler decided to add this local variable thing. This local variable thing is the stack protector, or more commonly, it is the canary. This is the canary in the coal mine. And the whole idea of this magic value, let's actually see this magic value show up in an example. GDB hello start display 8i RIP, and let's start stepping. Let's watch this value come out of memory. So we just pulled it out of memory, so it's in RAX right now. If we print this as hex, it is this thing. This thing, and every time you run this program, this thing will be different. But in this particular case, it is this truly random value. Truly random with the exception being that 1 byte, the very first byte, is a null byte, and we'll talk about why in a second. Oops. Wait, what? Oh, this is not a location memory. There's not a good way to print it. But we just pulled this random value out of this magic area of memory, and then we put that into RBP minus hex 8. So let's step here. And if we look at this location in memory as 8 bytes, because why not look at it as a different view? It starts with a null byte, and then it's truly just 7 random values in here. What this is this is the canary, and if you've ever heard of the idea of the canary in the coal mine, the idea is it kind of goes back to mining, that these miners, like actual people with pickaxes that go mining and stuff, they would bring these birds down to the coal mine with them, and if the bird suddenly dropped dead, that means there was a gas leak and they needed to get out of there. Like the mine is no longer safe. They would literally bring these birds with them. Maybe they still do, I have no idea. Probably they have modern sensors and they're not sacrificing these birds. They would bring this canary bird down into the mine with them. If this thing dropped dead, it's time to get out because you're next to drop dead. I don't know how long it takes between a bird to drop dead and a human to drop dead, but I'm sure as soon as you see that bird dropping dead, you want to get out. It's the exact same idea, just digitized a little bit. If this thing dies, and what it means for this thing to die is any of these 8 bytes change, the program is at some point in the future going to notice this and kill itself also. The program will die. I guess the metaphor kind of breaks down a little bit. But the program decides it's time to get out also. It's no longer safe. We need to abort mission. It's not just as soon as this is overwritten. it is at a specific point that we detect this. It's not like this part of the stack is like magical that if suddenly it's changed, like something notices and we panic and the program immediately dies. It happens, 20i RIP. It happens here with the epilogue. So at the end of the program frame, what we do is we take RBP minus hex 8 and we throw that into RCX. And then this is kind of convoluted. Maybe you understand what this XOR operation is. This is just a fancy way of doing a comparison. It's just checking if they're equal. Because what it's going to do is it's going to take RBP minus hex 8, and in theory, these 8 bytes have not changed from FS colon hex 28, this magical part of memory. If these things are identical, right, if it's the same exact value, when you XOR these things together, it's going to be a 0. So if they're the same exact thing, XOR them together, it's a 0 now. And then we do a jump if equal. If they are equal, we jump to main plus 9/8. So that means we're going to go to this leave ret. Otherwise, we fall through and we call into stack check fail, which is just going to terminate and kill the program. Now, in this small example, maybe it doesn't really make sense because it's such a small program. There was really no important stuff that was about to happen anyways. But as we already saw, actually, there was important stuff that was about to happen anyways. The potential for this ret was going to happen. We've already seen that with this ret and this buffer overflow, that we can overflow through and change the saved instruction pointer into the win function and call the win function basically through that. This canary right here stops this dead in the water. So let's go ahead and let's see this in action, actually. Let's take a breakpoint right here, and we will continue. And I will say hello, and then let's step. So print RCX is currently this. If we step again, we're going to XOR with what the original magic value is, the canary. If we print this, it's a 0 now, which means we are equal, which means if we step, we're going to leave retland, which is expected. Okay, let's start it from the beginning though. Let's do start. X20i RIP. Let's take the other case. Let's overwrite this canary. So we can see that our local variable on the stack that we're reading to is no longer RBP minus hex 8. That is now actually where the canary is. Instead, our local buffer is at RBP minus hex 10, so 16 bytes, which if we do the math right, this means that it's not a 16-byte offset to the saved instruction pointer, it's a 24-byte offset to the saved instruction pointer. And also, it's 8 bytes to the canary, which means that if I send like 12 characters or something, really if I send anything more than 8 bytes, I am going to be overwriting this canary. Let's see that in action. Let's break right before we do the read. Let's continue. Let's look at 32 bytes at RBP minus hex 10. Oops. Or, a better way of looking at this is 4 giant words. So we currently have this at RBP minus hex 10. Then we have this thing right here. This is the canary. Then we have just null bytes. And then we have our saved instruction pointer. As a reminder, if we look at this, this is libc start main or somewhere in libc start main. So we have these things on the stack. Let's go ahead and step. We're going to be first overwriting this. The first 8 bytes will go here, then the next 8 bytes, next 8 bytes will go here, next 8 bytes, etc. So let's step, or let's finish, and let's send it just a whole bunch of A's. We won't even think about it. Okay, and then let's print out our stack again. Right, we just blew through all of this with a bunch of A's, so now we have a whole bunch of A's on the stack. Everything just got overwritten. The canary got overwritten. The saved instruction pointer got overwritten. And let's just keep stepping, actually. We'll step over this puts. Now we're about to do this epilogue thing with the canary. So let's step instruction. So if we print RCX, guess what? This thing right here is our A's. And when we XOR it with what the original thing was, so this is an RCX, it's not 0 anymore, which means jump equal is not going to be true. And we're going to fall through to this call. So see, we're about to do the call. Let's continue. We will see that we get this cool message that says stack smashing detected, terminated. That's all that it does. If you ever call stack check fail, it just prints this message out to standard error and exits the program. That is what that function does. Literally just a message and exit. And if we want to see this maybe like outside of GDB, right, we send a whole bunch of A's. And same thing, right? Stack smashing detected, terminated. The program gets aborted, which basically means it sends the signal to itself. It sends the sig abort signal to itself, which induces the core dump in case you wanted to see as a debugger what's going on here. And the program is dead. So that's how the canary protected us. So we added that mitigation back, and suddenly this idea of control flow hijacking seems impossible. It does add constraints to what's going on. One thing that maybe you'll think doesn't sound possible, but I will tell you is possible, is what if somehow we manage to know the canary before that read call? If we somehow knew the canary before that read call, when we read all those bytes in to overflow past the memory or past our buffer and towards the saved instruction pointer, we could put the canary right back there. If somehow we knew the canary, we could put it there. So that's one thing to think about. If there's any way to leak out the canary before our memory corruption occurs, then we're fine. Of course, this does add like a pretty significant burden to an attacker, is somehow they need to leak out the canary. Before we dive into other ways that we can do it, actually, one other thing I'll show. This was a buffer overflow, right, that we were looking at. Maybe something that seems more realistic to you, though I will say there are ways to leak the canary as an attacker, depending on the program. It really depends on program behavior. Super small program, I mean, it's going to be tricky. Though one thing to think about, actually, now that I say that, is imagine we did this. We're like changing things, right? We just doubled our logic. Turns out that this program, we can bypass the canary problem now. Because what do we have here? So we saw before, when we put out our buffer, that under certain circumstances, those bytes were being read back to us, but past where we were going. So if we take this program, and literally all we did is we duplicated the logic. Why would someone write a program like this? I have no idea. But in theory, it's possible. And it turns out in real world software, these things get very complex. And something that looks like this does occur. It really does occur. And we recompile the program. We were in Emacs on this one. Let's go back. We recompile the program. And we run hello. And of course, we know that our normal mechanism, we send a whole bunch of A's. It tells us a whole bunch of A's and something. The question is, what is that something? We can do it again, and then it crashes. If we look at this, this is where understanding the layout of memory is super crucial to memory corruption. Understanding where all these bytes are on the stack is the most important detail. We've got our canary sitting here at RBP minus hex 8, and we have our buffer sitting here at RBP minus hex 10. So what happens if I send 8 A's and then I get a puts? It's going to puts whatever is there up until a null byte. Let's do that. Let's do that with Home Tools. Do I want to do it? No, let's do it in just GDB. GDB, hello. Let's start up the program. Let's display 8i RIP. Let's X20i RIP. Let's set up our breakpoints at these reads, or at least this first one. So let's break here. So right before this read. And then let's continue. So this is RBP minus hex 10. This is our buffer. So let's look at for gx at that location, right? We've got our uninitialized buffer here. We've got our canary. We've got, I don't know, other stuff. And then we've got our saved instruction pointer, same thing. Let's send 8 A's. So if we, next instruction, 1, 2, 3, 4, 5, 6, 7, 8. And there's a lot of things going on here. The specifics of this, the exact precision of this, everything matters. So when I hit enter, we're not just sending 8 A's, we're sending 8 A's plus a new line character, right? This is actually 9 bytes that I'm about to send when I do an enter here. And if you wanted to send exactly 8 A's without a new line, well, you're going to have to use something like pwn.college or redirect from a file, because guess what? If you press enter, you're getting a new line character when you run it in vanilla GDB, just like this. And what that means is we're about to put 8 A's right here. This is going to be completely overwritten with A's. And then the very next byte that's going to get overwritten is this 0, 0 right here. This, remember, it's a little endian integer. The least significant thing, that is the first thing. We're about to overwrite that. So let's do that, and let's confirm that I'm not making stuff up. So we've got our 8 A's, and then we've got a 0A here, and then we've got more stuff here. If I now go all the way to this puts, so let's break on puts, and we continue, and we print out RBP minus hex 10, because that's basically, this command in GDB is basically the equivalent of puts. X/S means just keep printing bytes to me as ASCII until we get to a null byte, which is what puts does. We get a new line character, and then, I don't know, it depends. I have no idea what that thing is. I guess it's what? It's all right, amazing. And then more bytes, and realistically, this is not my favorite way of looking at this. So instead, we'll do 20 bytes, and just know that these bytes are coming to us until, so we have our 0A here, then we have D9, BC, A1, DA, 57, A1, DE, and then our null byte. Guess what all of this right here was? This is 7 bytes of our canary, and we know what the 8th byte was that we overwrote. This was a null byte. So in just duplicating our simple program to ourselves twice, we have this puts mechanism, and this puts inevitably just leaked out the canary to us. We now know the canary. We'll see, we can script this up with pwn.college to know it. Just know these bytes are really coming to us. When I hit next instruction, it's not going to look very good, right? It's not a very exciting view. I mean, maybe I can copy these things or something. But if we use pwn.college, we'll really be able to see those things. And then, as we continue on, it's going to puts hello world again, and then it's going to read again. It's going to read and ask for another byte. It turns out this is another same buffer overflow going on here. But now I know the canary. And now if I feed the canary back to it, I will have just corrupted the canary, because this null byte really does matter. You can't just modify one byte and say, like, hey, the bird's just like ill or something, but we're going to continue executing. The canary did also just get killed here, but we can put the canary, we can bring it back to life. I think there's a question. Yeah. Yeah, the canary gets set at the start of a function.
So like, how does it get modified? It gets modified.
Yeah, it gets modified during the function because we sent 8 A's. So this 8 A's followed by a new line character. And that new line character, where that's going to memory, corresponds to the first byte of the canary. Yeah, because it's at the buffer is at RBP minus hex 10, and the canary is at RBP minus hex 8, which means 8 bytes, and then the very next byte is the first byte of the canary. So all these things are like, I mean, they're like all semantically different things, but they're all just sitting on the stack in memory, all sitting next to each other. And like, if you start doing weird overlapping stuff or buffer overflow, right, you're overflowing into other semantically important things. And based on how I've been interacting with it using GDB, I have no hope of sending it the canary. But if we use pwn.college, we'll see we did in fact just get the canary. So let's do that. So if we want to confirm that this really does work, what we can do is we can say our payload is 8 A's, and then we'll just say it can be anything here, right? I guess one other thing I'll detour to. Remember how this was a null byte? The first byte of the canary is always a null byte. The reason it's a null byte rather than getting one extra byte of like randomness entropy, because in theory, right, if we sent a null byte, we would be guessing and overwriting one byte of the canary. And we're not guessing because we know it's a null byte. The reason it does that is exactly because of what's going on. That one of the dumbest ways to get a leak is if you have a whole bunch of bytes just sitting there and you overflow and you don't put a null byte at the end, right? The way that we're doing this is we're using this read system call, and you don't need to end with a null byte. But if you use something like gets will put a null byte at the end. It's because in C, like, it's very common to not pass around sizes and instead pass around these null terminated strings. And if you then go on to puts that thing or you output that thing, this byte normally being a null byte, it stops this like puts leaking mechanism normally. Of course, we didn't use gets, we used read, which meant that we were able to overwrite this null byte. The reason it's a null byte is it stops a lot of the leaking mechanisms by, if you're just going to start outputting until you see a null byte and you're not able to overwrite this thing, it'll just stop there. Because you could imagine instead that maybe I didn't have a buffer overflow here. Maybe I just did read and I read 8 bytes. If this thing wasn't guaranteed to be a null byte, but then we went on and we putsed this thing, let's say I had 8 A's here, and then this was just a random byte, whatever the other random byte would have been of that canary. Still, if we putsed that thing, we would have leaked the whole canary to ourselves. Even without memory corruption here. We could have been totally valid, read 8 bytes in, putsed it, and just because they're sitting next to each other and there's no null byte, it would have gone all the way through. So that's why that's normally a null byte. Of course, we're circumventing this because we do have memory corruption here. Okay, let's see now how we can do this. So we're going to overwrite that null byte here. This B here is going to replace the null bytes. Let's write the payload. And before we write the payload, let's go ahead and p read line will just, well, we won't print it. We know that it's saying hello world first, right? This line is going to read in that hello world. We're going to write the payload, and then let's do p read line. And we'll just start with that. So what we just did here is we read this whole sequence of things in, right? And we can see we have, if I assign this to a variable, we'll say canary equals that thing. I now know the canary. Of course, the first 7 bytes, or the first 8 bytes, I should say, are just my A's. Everything after that, we have our B character, so maybe we'll just skip over that. Now we have this thing right here. The length of this is, well, it's actually 8 bytes, but we only care about the first 7 bytes of that thing. Because if we think about how memory is laid out, we have our B character that replaced the null byte. We're printing everything past that. So we'll say, maybe to make this even clearer, say 8 plus 1, right? This is going past the 8 A's plus of that one B character. And then there's 7 more bytes, and those are the random bytes. So this right here, this is our canary if we put a null byte back in the beginning. This is our canary. So it's, I mean, maybe this looks a little contrived or convoluted and we're doing like these weird offset calculations, but we just had it leaked to us and we can reconstruct the canary by doing this. This is now the canary. What we can do is we can do p.write 8 A's plus this thing, because remember we're about to do a second read, or actually let's do p.read line real quick. Hello world, so we're back here, and then let's print out C times 20 or something, and then p read all. And we see we did not sig abort. We did not get that canary issue. We got a seg fault. The reason we got a seg fault, of course, because we overflowed save instruction pointer with a bunch of C's. but we can see that we were able to give the canary back to the program, kind of resurrect the bird, and continue executing just fine. All we had to do was leak the canary. In order to leak the canary, it depends on the specifics of the program. In the next class, we'll talk about other ways that you can get memory corruption that aren't just a buffer overflow, where in theory you could just skip past the canary and never touch the canary in the first place and just go straight to saved instruction pointer. So a whole bunch of things. And then also in the next class, we'll talk about the other mitigation, which is pi. All right, cool. Thank you everyone for attending and good luck.